Alright, so as always, it's probably a good idea at this point to pause the video, read the problem statement so that you can come up with your own perspective on how to solve the problem. And we're back. Okay, so in this problem we're dealing with exergy. We've got an ideal gas, we've got air, and we're treating it as an ideal gas with constant specific heats also. So one of the things that happens in this problem is we get to review our substance model for how to deal with ideal gases with constant specific heats. So we have a two-step process, constant pressure followed by a constant volume. We'd like to know all sorts of things. In this video solution, we're going to focus on part A. We're not going to do part B using the tools for part B, which is energy conservation and entropy accounting, but we are going to find the total useful work out and the maximum possible useful work out of the air, but we're going to do it using the methods of part C, that is using an exergy approach instead. I would encourage you to see previous examples about how to work this problem using the energy entropy accounting approach instead. In any case, here's what our PV and TS diagrams look like respectively. These lines on the diagram, right here in the PV diagram, are lines of constant temperature, and each one of these up and to the right of the previous one is a larger temperature than the one before that. You can figure out the shape of that curve from PV is equal to RT. Not the exact shape, but certainly the trends involved. So that's how I knew that from 1 to 2, besides being on a horizontal line, since it was constant pressure, I knew that point 2 was to the right of point 1 because temperature 2 is bigger than temperature 1. Likewise, for point 3, I knew that 2 to 3 was a vertical line on a PV diagram, but to know that 3 was above 2, I used the fact that given in the problem statement, the temperature of 3 is greater than the temperature of 2. And here's your TS diagram. The lines of constant pressure and constant specific volume on a TS diagram are both kind of catty-cornerish, one steeper than the other. You can show that using the appropriate equations, but I don't think it's as important in this problem as a PV diagram. So if you got this piece correct, that's the major thing that we're looking at. Okay, so let's move on to part C, which is to find the total useful work out of the air and also the maximum number that could be using an exergy approach. So here we have our piston cylinder. It's got air in it. Heat transfer goes into the air in a two-step process. That heat transfer comes from a reservoir at 300 degrees C. It does not come from the surroundings, and then the work is done on something that we don't see, I guess the surroundings if you'd like. So to find the work, we're going to use our good old integral of P dV. That's going to be the work out of the process. And I can go from 1 to 3 in steps. I can go from 1 to 2, and then from 2 to 3, reminding myself what my PV diagram looks like. I see that 2 to 3, being constant volume, has no work out, and all the work is from 1 to 2. And I've conveniently picked a closed system, so I can use this integral. So I can take M out of this, and I've also conveniently picked this to be a constant pressure process, which means I can pull P out of the integral, and I have simply the integral of dV, which is nothing more than delta V. So I'm in good shape here. If I can only find V1 and V2, since I'm given M and P1, I can get a number for the work out of the system. So remember, we're dealing with an ideal gas with constant specific heats here. So far we've been using steam quite a bit. We've been using the steam tables or E's or other things to find our properties. I do not find V using property tables for an ideal gas with constant specific heats, okay? Or even an ideal gas with non-constant specific heats. I use good old PV is equal to RT, and I solve that guy for a V. So that's how I find V here. I have to calculate it. Now when you go through this calculation, remember that you need absolute temperature in this equation. You cannot use degrees Celsius. So that'll give me my V1. And also remember that in this equation, PV is equal to RT. That R that we're dealing with is not the universal gas constant, 8.314 joules per mole Kelvin. This is on a per kilogram basis. So to get that, you have to divide the universal gas constant by the molar mass of your gas. You'll probably memorize what that number is for air because we use air quite a bit. So in any case, I find V1 and V2 using the ideal gas equation. and I plug those guys in and get the work out of the system. Now remember, not all work is useful. Part of the work is used simply to move the atmosphere out of the way, and only the work above and beyond that is of any use to me. So to find the useful work out, I'm going to subtract P delta V, where P is of the atmosphere itself. So that part of the work is not useful to me. I subtract that off, knowing both V1 and V3, because V3 is exactly the same as V2, and I find that half the work approximately involved in this process is wasted simply moving the atmosphere out of the way, but half of it is useful to me. So there's the work out of the system and the useful work out of the system. Okay, so next, although this is not explicitly asked for, I'm going to apply conservation of energy to find the heat transfer. I'm going to need that number at some point. So I see a system that goes from state point 1, things happen to it, and then it ends up at state point 3. This is a closed system undergoing a finite time process. If I additionally ignore kinetic and potential energies, the resulting form of conservation of energy is that the change in internal energy is the heat transfer in minus the work out. This is, in fact, the total work out of the system. All right, that guy is not equal to the useful work out. The conservation of energy accounts for all energy, not just the useful part. That'll change when we look at exergy, okay? But conservation of energy needs all of the work, not just the useful piece. So there's my conservation of energy equation. I put that in terms of little u and mass. And then I invoke the idea that this is an ideal gas with constant specific heats. Hopefully this looks familiar to you. The change in specific internal energy for an ideal gas with constant specific heats is C sub V times the difference in temperature. So I don't have as much work to do here in terms of finding properties when I have an ideal gas with constant specific heats. I can use lots of equations instead. I know everything in that equation: mass, specific heat, the temperatures, and the work, which I just calculated. So I plug those in and find almost 50 kilojoules worth of heat transfer into the system. So very good now. So if this were part B, I would have done part B1, and to find the maximum possible useful work out of the air, I would write the accounting of entropy for this system. I'd find the entropy generated during the process, and then add T0 times Sgen to the work that I had to find the piece of it that was lost. If I'm going to use an exergy approach instead, what I'm going to do is write the accounting of exergy for the system, and in order to find the maximum amount of useful work out, I'm going to set the destruction of exergy to 0. Let's see what that looks like. So here's my system. Things happen, and then it ends up at state point 3. Notice that when I say things happen this time, I'm drawing the diagram to show the flows of exergy. So this guy is heat transfer in, but it's multiplied by 1 minus T0 over TR to show what part of that heat transfer is actually has an exergy content. Not all of that energy is potentially useful to me, only a fraction of it. Also notice that I'm drawing the boundary here as TR. This is the temperature where the heat transfer is crossing my boundary. That's vital to figuring out what the exergy of that heat flow is. Also notice that I'm drawing work out of the system, but only the useful work, because again, exergy has to do with useful work. It's not all the energy. It's not all the work. It's only the useful part of it. So this is my diagram of what happens between 1 and 3. Those are the flow of exergies. There are no destruction terms of exergy for the maximum amount of work. There's my general accounting of exergy. Good for any system in the entire universe. I've gotten rid of the m dot AF terms because this is a closed system. And the next thing I'm going to do is integrate it with respect to time, because I'm going from 1 to 3 over a finite time. I'm not looking at a rate basis. So on the left-hand side, I multiply by dt, and I get dA. Integral of dA is delta A. On the right-hand side, when I integrate q dot dt, I get q with no dot. Same thing for the useful power turning to useful work. And notice that I have set the destruction of exergy to 0 in order to find the maximum value of W1 to 3 out of the system. So solving this guy for W1 to 3 useful maximum, again, I'll emphasize that this is an important piece here. I'm dealing with the maximum amount of work or useful work out of the system. I find that I have everything I need here to calculate this number. So Q is already known. I know these temperatures. I have M. I need A3 minus A1. So remembering that A is U plus P naught V minus T naught S, I see that in this case, since I'm finding a change in specific exergy, that I can take a shortcut. I don't need to find U0, V0, and so on. I can find the change in specific exergy from 1 to 3 directly by finding U3, U1, V3, V1, and so on. So a little bit less work for me in this specific problem. Okay, so again, we're dealing with an ideal gas with constant specific heats, and I hope these formulas are becoming familiar to you once again. So delta U is my C delta V, or C sub V delta T, sorry. V3, V1 I've already calculated from the ideal gas equation. And this guy, the delta S, the change in specific entropy, in this case is most conveniently calculated by C sub V times the log of the temperature ratio plus R times the log of the specific volume ratio. There's another equation you can use. This one's the most convenient in this case because I already have all the numbers to go into that. Be careful about absolute temperatures once more. That must be an absolute, the temperature of the surroundings. And so must that guy. Okay, so that ratio of temperatures in this equation to find specific entropy, those temperatures must also be an absolute. And plugging and chugging, I find that the useful, or the maximum amount of useful work out of the system going from 1 to 3 is 16.1 kilojoules. Okay, I got 5 kilojoules out. It could have been 3 times that amount. So once again, I see that exergy destruction has hurt me. Now there is another approach to doing this. Okay, and maybe this is one that you came up with. So I went from 1 to 3, applied the accounting of exergy to it, made it finite time, and set the destruction of exergy equal to 0 so that I could find the maximum value for 1 to 3's useful work. Okay? Another approach would be to do this, to actually write the accounting of exergy for the real process, okay, where there is the destruction of exergy. In that case, I would use the value of the useful work 1 to 3 that I've already calculated, the actual value for that, and then solve the exergy accounting equation for the destruction of exergy that happened between 1 and 3. Completely legitimate way of doing it. The Q doesn't change, the A1, A3, that doesn't change. And then, now that I have the destruction of exergy, I would add that destroyed exergy to the actual useful work, and that number will also be equal to the maximum useful work out of the system. So there's a couple ways to approach this problem. Both of them are equally as valid. But the important points are that you understand what the terms in the accounting of exergy mean and how to apply them for a specific system so that the numbers you get are meaningful. Okay, so that's the end of the problem, but let us very quickly remind ourselves what these equations for ideal gases with constant specific heats are. We're going to be using the substance model much more in the days to come. So let's start with good old PV is equal to MRT. Or P little v is equal to RT. These are the convenient forms for many engineering calculations, but remember that the R that we're dealing with here is not the universal gas constant. It is the universal gas constant divided by the molar mass of the gas at which you're looking. Here's an equation that you may or may not have seen before. I can calculate C sub P from knowledge of R and C sub V, or C sub V from knowledge of R and C sub P, or R from knowledge of C sub P and C sub V. So when you go to look up C sub P or C sub V, you might only find one number given. And the reason for that is the place where you're looking up is assuming that you know how to relate C sub P, C sub V, and the ideal gas constant to each other. So other equations, delta U is C sub V delta T. We use that in this problem. Delta H is C sub P delta T. We use that in this problem also. And there are two equations for the change in specific entropy. There's this guy that's got specific heat at constant pressure and the log of pressures in addition to the log of temperatures, or ratio. And then we also have this guy, which we did use in this problem, where we have the log of the temperature ratio, and the log of specific volume ratio instead. This is a plus, That's a minus. That's C sub P. That's C sub V. These will give you the same number. Which one you use depends on what's most convenient for you to use in a particular problem.